Hello everyone. Today we have Kähler Pawar, who is a postdoc at IISER Pune. He will speak on the Hodge theory of compact Kähler manifolds. Rakesh has did his PhD from Tata Institute of Fundamental Research in 2017. After that, he held postdoctoral positions at University of Essen, Germany, and then IISER Mohali. Rakesh has written multiple papers on the filtration on cohomology and zero cycles. His thesis was based on the action of correspondence on cohomology and zero cycles. So today he will speak on the theory of compact Kähler manifold, which will be needed in the Calabi-Yau theory in future courses. So over to you, Rakesh.
Okay, thanks. Thank you for the invitation and generous introduction. Okay, so my goal is to talk about to actually prove the theorem that there's a decomposition of singular cohomology of compact Kähler manifolds, and it has a structure of it has a Hodge structure on it. Okay, so I will start with a complex manifold of dimension n. So some preliminaries. So the strategy is going to be complex manifold has two structures. One is a complex manifold. So locally, it is given by a holomorphic chart, open subsets which are holomorphic to open subsets of Cn. And so that the transition maps are holomorphic. And there is another structure on it, which is you can think about C as R2 and think about complex manifold as a real differential manifold. And now we'll play with these two structures to understand the singular cohomology of the underlying topological space with real coefficients and with complex coefficients. So both these structures will play the crucial role of coming up with the Hodge structure. Okay, so let me fix some notations. So suppose, given the complex manifold, there is a cover given by ui phi I, where ui's are open subsets of X. And there are maps from UI to Cn, just so that it is homeomorphism onto the image, such that if you look at the transition maps, so on the intersections, if the intersection is non-empty, there are two maps, phi I and phi j, and look at the transition map from phi I of UI intersection uj, which is open subset of Cn, to open subset of Cn. So I can talk about holomorphicity of map from open subset of Cn to Cn. And in that sense, we say that these phi's are with the property that the transition functions are holomorphic. So that's a structure on X as a complex manifold. Now we can write down, so Cn we can think about as coordinates with coordinates z1, z2, zn. And we can restrict those coordinates on each of these open subsets phi of u. Now we can think about these transition functions, which are now holomorphic from open subset of Cn to Cn, given by tuples f1, f2, fn, where each fi is now a complex valued c-valued function, and each coordinate function is holomorphic. And now we can think about the tangent space of the complex manifold at X in terms of the basis with given by partial d by dz1, d by dz2, d by dzn, where z's are the coordinates on phi of u. Okay, so we want to think about the tangent space, which is a complex vector space with this basis over C. And on the other side, we want to think about complex manifold as a real differential manifold, where we want to think about this Txx, which is a tangent complex vector space a priori, as a real vector space with a different basis. Okay. So we think about Cn as R2n. We want to think about, let me just move some. Yeah, so we want to consider the real manifold with the same chart, ui phi I, but want to think about phi I as not as complex valued, but as R valued functions, tuple given by R valued functions. Such that again, the image is homeomorphism onto an open subset of R2n, and the transition functions are now from open subset of R2n to R2n, and we demand that so we observe that the component coordinate functions are C infinity functions. And now we want to think about so what is the corresponding coordinates? So for Cn, the coordinates are Z1, Z2, Zn, and on R2n, the corresponding coordinates are, so we write Zn, Zz as xj plus iyj, and think about the coordinates x1, x2, xn, y1, y2, yn as coordinates on R2n. So we can now think about these functions as giving real valued functions from this on these coordinates. So we think about so let's write down some functions. This fr, we write the real part and imaginary part. These are R valued functions which are C infinity, and these are not general any arbitrary R valued C infinity functions. Since these fi's are holomorphic, this will force us to show that force that these FRs form a particular set of equations, differential equations called Cauchy-Riemann equations. So partial of UR in terms of xj is a partial of VR. So VR is second coordinate for yj, and the partial of UR with yj is minus of VR with dx. So this will come from the fact that being holomorphic is saying that d by dz bar of f is 0. Right, and in terms of the tangent vector space, so it's the same tangent space, same vector space, but think about it as a R vector space, with now the basis is given by d by dx1, d by dx to d by dx and d by dy1, dy1, and now there is a relation between these complex basis vectors and these. If you want to think about as a tensor with C, there is a relation between these two. Okay. So, so to make this matter slightly more clearer, we will think about a complex manifold X. I write XR as the corresponding real differential manifold with there's something called almost complex structure, in the sense that the real tangent bundle. So this is a real vector bundle on XR. It has a endomorphism as a real vector bundles, such that Z square is minus identity. Okay. So I want to make it more explicit in terms of the basis vectors that I gave. So let's say you fix a point, and so you fix a some chart, holomorphic chart, u comma phi, as earlier. So phi is the map from U to Cn. And now to think about this complex vector bundle Tx on U cross Cn on the open subset U. So I can identify with U cross Cn with the vectors, with basis vectors given by d by dz1, d by dz2, d by dzn. Okay. Similarly here, and this Z map, which is a map from this real vector bundle Txr to itself. So what is it doing? It is actually sending the local basis vectors d by dxz to d by dyz, and d by dyz is minus d by dx. Okay. So this is an explicit endomorphism, and you can check that if I take z square, it is minus identity. And now what we are doing is thinking about sending this Txr to Txu as a map of real vector bundles, which sends d by dxz to d by dzz, and d by dyz is I times Txz. So what it is, or what all it is doing is that if I go to if I tensor this Z with C, okay, then on this Z is acting as multiplication by complex number psi. So it is sending d by dzz, a basis vector, to I times dzz. Okay, so there's a sort of, in some sense, it's a I eigenspace, or eigenspace with eigenvalue I as a subspace of this after tensoring with C. Okay, that is the idea. Right, so I have a Z, which is an endomorphism of this real vector bundle. I tensor with C, I get a complex vector bundle. So Z tensor identity acts on it. And now since it's a complex vector space and Z square is minus identity, it has eigenvalues I and minus I. So I can talk about I eigenspace and minus I eigenspace. So I decompose this vector bundle. So here it's vector is a tangent space at fixed point. I will break into two pieces. T1, 0, I will call it as I eigenspace. So where Z acts as multiplication by I on this. and on this z acts as minus multiplication by minus I. Okay. And now, as I said earlier, this with the choice of basis that we took, Txx, the complex tangent bundle, can be seen as a sub bundle of this complexified real tangent bundle as the eigenspace with eigenvalue I. So it can be identified with this. So you can think about the complex tangent bundle as sitting naturally inside this complexified real tangent bundle. Okay. So now what to do is we take the dual. Just take the dual home comma C. So this is omega x are just dual of this as a real vector bundle. I tensor with C, and this is the corresponding dual. Okay. And I take the, so this is a complexified real vector bundle. I take the kth wedge product, and I use the usual formula of taking the wedge product. This is the alternating sum, and we'll write this pth wedge product of omega 10 tensor with qth wedge product of omega 01 as omega pq, and sum over terms with p plus q equal to k. So this is just some explicit linear algebra. But now in concrete terms, what is this? So we want to explain what the sections of these vector bundles are locally. So let's say U is an open subset of X. Then I want to denote AK of U as the sections of omega. Oh, I should have written lambda k of this. Okay. So AK of U are sections of U of this vector bundle. That's what the k is. So here it should be lambda k of omega x tensor C. And similarly, APQ of U, I want to denote them as sections of this vector bundles. Okay. Now in terms of coordinates, in local charts, what we do? So let's say coordinates z1, z2, zn on U, and let's write dzz as this dxz plus idyz and dz bar as this, and you can write down the elements of APQU. These are exactly C infinity U modules. So this is C infinity U is all complex valued differential functions on U. So this is a ring, and I want to take the module generated by sections, which are this dz. So you take p many differentials in terms of the coordinate zz, and take the q many differentials of the anti-holomorphic ones, dz bars, and take q wedge product of those, and take the p wedge product of those. So that's what the p and q is. Okay, so this will exactly come from this explicit description of this. Okay, so omega 10 is generated by as a C infinity module generated by dz1 or dz i's, and this is generated by dz I bars, dz bar i's. So you want to think about elements of APQ as a linear sum of some function defined C infinity function on U times this basis vectors. Okay. Now we want to go to the I want to define the Rham cohomology of a complex manifold. So we start with the complex manifold. Let U be open subset. Denote A0 of U as C infinity of U. Just C valued differential functions on U. And now what we can do is we can just form this corresponding complex where D is a differential. So C is the complex numbers, A0 is C infinity of U, A1 U as defined earlier. Right, these are k-linear C-valued differential forms, and you can there is a differential. You can differentiate functions, and you form this complex, and you can check that decomposed is 0. So for every U, you get a complex abelian groups, and we'll just declare that Rham cohomology of X with coefficients in C is a degree of kernel of at the degree k modulo the image. It's a cohomology of the complex in degree k. Now this is called Rham cohomology group, and we can take the direct sum. It forms a graded ring, with product given by, you can wedge two differential forms. Take a wedge product of two differential forms, and you can check that if you take elements in the cohomology groups, two elements in the corresponding cohomology groups, take the wedge product, it gives a cycle, and you can take a well-defined element in the cohomology group, and that will be our definition of product. Now it turns out that so since it certainly depends on the differential structure of the manifold, complex manifold, it's a diffeomorphism invariant. So if two things are diffeomorphic, you get the same cohomology groups, also with the graded ring, graded structure. But it will turn out that it's a topological invariant. So even if there are two topological spaces which are homeomorphic but two different diffeomorphism structures, differential structures, then you still get the cohomology groups as isomorphic. Okay, so now there's a Poincare lemma which says that if you take a contractible open subset on X, then and you calculate the cohomology on U, the Rham cohomology, then it vanishes, right? So this is saying that this complex is exact. Yeah, that's what it's saying. This complex is exact. And from this, what we can conclude is that if you think about now this AK defining a sheaf on the topology of X, then this AKs form sheaves, and you are now getting a complex of sheaves of abelian groups, and it will turn out that this AKs are something called fine sheaves, so they're acyclic, so they don't have any higher cohomologies, and since because of the Poincare lemma, you get a resolution of this constant sheaf. So I can write 0 to C to A0 to A1. So I will just drop U as a complex of sheaves, which is exact. So I get that if I drop C here, I get a resolution of C. And now some sheaf cohomology theory will tell you that the kth cohomology of the constant sheaf C is exactly the cohomology of the complex with the Rham complex. Okay, so that's how you get this. And there is a separate argument to show that the singular cohomology of X, which is defined in terms of topological singular chains and so on, complexified singular chains, it will agree with the sheaf cohomology of the constant sheaf. Okay, so this is a separate argument. So what we can do by this is that Rham cohomology will identify with the singular cohomology. And now this is a topological invariant. That's how the Rham cohomology is a topological invariant. Okay. Right. So now the next ingredient is going. So now till now we just use the fact that we just observed that there is a Rham cohomology of X complex manifold, which is defined using the differential structure, and we have identified with the singular cohomology of X, which came from the topological structure of X. But now we want to use the complex manifold structure underlying, which is there. We still haven't used it, and that's where the Dolbeault cohomology will come in. So let's look at the differential from AK of U to AK plus 1 of U. So it sent C valued K differential forms to C valued K plus 1 differential forms. And now we observe that AK of U had different components. So if you remember, right. So sections of this, which are AKU, will decompose into sections of this, which are APQ of U. Right. So if I have a differential from AK to AK plus 1 of U, I will write the so if you look at the differential and evaluate on P comma Q differential form. So I gave an explicit description of what the differential form looks like. DZ1, DZI1, DZIP, which DZ bar I1 to DZ bar IQ. And if you evaluate the differential, it will land in these two pieces, P plus 1 comma Q and P comma Q plus 1. Okay. So I can write down this differential as a sum of two differentials, this del and del bar. Okay. So you can think about del as a differential coming from del by DZ, del by del or D by DZ, and del bar is coming from D by DZ bar. Okay. And now D square equal to 0 will imply that this components, they will form a complex. So del bar square is equal to 0 and del. Okay, I always have difficulty saying what is that. So del square and del bar square. Okay, and further del compose del bar plus del bar compose del is 0. Okay, this is going to be important. And now we can see, since this identity holds, I can form a new complex. So what I will do is I will start with AP0, right? And if I apply del bar, this is telling me that AP0 will go to AP1, right? And I continue where n is a dimension of x, capital X. So I'll get this complex, and we already checked it's a complex because del bar square is 0. Now, if you calculate the kernel of this del bar is exactly degree P holomorphic forms. These are exactly the so if you take any del bar of something is 0, will exactly give you a differential form of the type dz1 wedge dzp. There won't be any component coming from dz bars. Okay. So this is a complex for every u. And I will say, if you take the qth cohomology of this complex with the partial del bar, we are going to call it Dolbeault cohomology. Okay, this is the definition of. So cohomology in degree q is the Dolbeault cohomology of X, and we'll denote it as HPQ, where P coming from because it starts with the AP. Okay, so now there is an analog of Poincaré lemma here. So what you do is you take some fixed tuple of complex numbers A1 to n, and look at this polydisk. So this is a disk in Cn, where the distance between the complex value of Zi minus Ai is less than epsilon. So it's a n polydisk with the center A1 to n. And if you calculate this, if you evaluate this complex on this particular open subset and calculate the cohomology, it will be 0 in positive degrees. Okay. So this is analog of if I took del bar to be the usual D, that was the classical, that was the usual Poincaré lemma. And this is a Poincaré lemma with the differential del bar. Okay, so as we did last time for usual differential, this tells me that for this contractible open subset U, this complex is exact. So I can do the same thing. I have X complex manifold with the topology given by these open subsets, and this APQs will form fine sheaves, and they'll be acyclic. So I get a resolution of omega px by acyclic sheaves of abelian groups. So I can calculate the cohomology of omega p in terms of the cohomology of just evaluating this complex and taking the global sections. Okay, which is exactly this right hand side, taking the calculating the cohomology of the global sections applied to this complex, and left hand side is the cohomology of the sheaf omega. So what we have done is that we identified the qth cohomology of the omega p holomorphic differentials in terms of the Dolbeault cohomology. Okay, so right. So let's keep whatever we have done aside for a bit, and now we want to put a more structure on complex manifold. So this is the best you can do. You started the complex manifold. You identified you wanted to start with singular cohomology of X. So using the differential structure, you identified with the Rham cohomology on one side. Using the complex manifold structure, you identified particular sheaf cohomologies of HQ omega p with Dolbeault cohomology. Now let's put more structure on complex manifold. So I want to consider a compact complex manifold with the Hermitian metric. So what I mean by that is X is a complex manifold. For each X in X, there is a bilinear form on the complex vector spaces. This is just a complex tangent vector space. So this is a bilinear form with the property that it is sesquilinear in the sense that it is C-linear in the first coordinate and anti-C-linear in the second coordinate. Okay. Also, I want it to be positive definite and the property that HUV is complex conjugation of HV comma U. So this is just saying that. So capital X with a continuous in the sense that so this is for every X there is HX, And also I want this hx to behave very nicely as a very x in different coordinates. Okay. So we will say that with that structure, we'll say it's a compact complex manifold with Hermitian metric. Now what we can do is, since for every pair I get a complex number, I can write it as a real part and a imaginary part. So I will decompose this H as a G minus I times W, where G is some real number for every pair, every tuple, and I will write W, which is the minus of the imaginary part of H. And it will turn out that with these properties, this real part will form a Riemannian metric on the underlying differential manifold. Okay. And what is this W? So this W will give me an alternating form on this complex vector space with the R-valued function. So it's an alternating form. So V comma W is minus. So if you evaluate on the tuple U comma V, whatever you get will be minus of whatever you evaluate on V comma U. So what you get? So I want to think about this complex vector space as a real vector space now. So that's why this. Right? This is just the same vector space. Think about it as a real vector space. Now, if I think about as an alternating form on this real vector space, I can think about as a element. It gives a well-defined element in lambda 2. So this is a wedge product of this real vector space, the second wedge product, right? Dual. And I complexify it. So I identify this with lambda 2 of TXR tensor C dual, which is exactly lambda 2 of omega XR, which is a dual. This is just a definition. This identified. Okay, so what I'm getting is WX as an element of second wedge product of this vector space, differential forms. Okay. Now, if you remember, so again, the earlier calculation, we had some K wedge product and we broke it into pieces. So the K, this will break it into pieces where it will be 2, 0, 1, 1, and 0, 2, right? And now it will turn out, so a priori this WX element will give me an element here in this direct sum. This is a direct sum of pieces with a component 0, 2, 1, 1, and 2, 0. But it will turn out that actually W will land in 1, 1 piece. So it doesn't have 2, 0 and 0, 2 components. Okay, so it's some checking that one has to do. And moreover, since it's a real valued, W conjugation is same as W. Okay. Now this is quite special in the sense that so this just I'm just recording it. So W will give a section of X in the A1, 1. So let me just again recall the definition of A1, 1. Just for right. So I had this. I got a W as element in lambda 2 of this, and I break it into pieces. There will be W omega 2, 0, omega 1, 1, omega 0, 2, and I'm setting a W as a section in the middle piece, omega 1, 1. And that is the element of A1, 1, right? This is a A1, 1 of U of X is a section of this omega 1, 1. Right. Now, I want to define a complex manifold with a Hermitian metric. I want to define it as a Kähler manifold. If this Hermitian metric H, there is a Hermitian metric H, which is Kähler in the sense that this alternating form W, right, which is now you can think about as an element of A2 of X, and there is a differential. If we evaluate D on W, it is 0. So it's a closed 2 form. Okay, so that's a definition of that's when you say. So X comma H is a Kähler manifold if omega, which is the minus of the imaginary part of this Hermitian metric, is a closed 2 form. Okay. Right. So now we will employ this Hermitian metric to. So let's say start with the complex compact complex manifold dimension n. There is Hermitian metric. Now you look at the XR, which is underlying differential manifold. Now there is a non-trivial operator that is going on at the differential forms level. So it's called Hodge star operator. So this is very explicit. What you do? So this, if you remember, we didn't use the Riemannian metric. So H had a real part and imaginary part. The real part formed a Riemannian metric on the underlying differential manifold. So that G gave a alternate bilinear form on this omega lambda k wedge kth wedge product of omega x. So you should think about G as this tensor this to R. So I can think about this as a map, giving a map from this to dual. So home omega k comma R. And now what to do is, since it's an oriented manifold, you can identify this, the top wedge product, because it's X is a 2n-dimensional wave manifold with R, and this is the identification, right, in the home. And now what you do is, now this is the bilinear product coming from the, this is the isomorphism coming from the wedge product of differential forms. So if you take any 2n minus k differential form, and you want to define a linear map like this from here to there, you just take some beta and just wedge that to get a 2n degree differential form, and it will turn out to be isomorphism. So what I'm getting an operator from kth differential forms to 2n minus k differential forms. Okay, now I complexify this. So this is just this original star tensor with C. Now this will, if I can put them together to get, so on sections, if I evaluate the sections of this on X, I can define using this star a metric on this vector spaces. So what is a metric? You just take alpha, which is a differential k form, and beta, which is a differential k form. You apply the Hodge operator, right? You get a 2n minus k differential form. So this is a degree k differential form. This is a star beta is a degree 2n minus k differential form. Take the conjugation, take the wedge product, and take the corresponding element. So this will give a total element in lambda 2n omega xr, and take the corresponding real number, corresponding x complex number, because we are complex event. Okay. So I'm getting, so what I've done from the star operator, I'm getting a metric, some sort of metric on these vector spaces. Okay. So let's put all this together. Whatever we have defined so far, let's put all this together and see what we get. So using the real manifold structure, I have this star operator, and using the star operator, there's a metric, and I can define an adjoint with respect to this metric, in the sense that if I take d alpha beta, it is just alpha comma d plus star beta. Okay, this is just a usual adjointness of operators with respect to if there is a metric on the vector space. So there is such an operator which is explicitly given like this. So you just apply star d star inverse particular sign. Right, and now what we can do is if you put this together and form this decompose d star plus d star compose d. Okay, and think about this operator now from ak of x to ak of x. You can check a degree k form goes to degree k form, the way it is defined, and this will turn out to be Laplacian. This is called Laplacian. And what to do is, okay, so now let's use the complex manifold structure. So if you remember, the complex manifold structure broke this differential d into two pieces, right? And again, using the Hodge operator, which came from the differential manifold structure, I can define adjoints of these del bar and del bar, del star and del bar star. Okay, some explicit formula. Now what you can check is that let's form these operators, differential operators, with respect to these adjoints. Again, adjoints in the sense of there is a similar identity. So if I apply del alpha comma beta, that is alpha comma del bar or del upper star beta. Okay, it's the same adjoint relation. Okay, I have not written it for this. And using these partials, I can form two differential operators, partially Laplacian with respect to del and Laplacian with respect to del bar. And let's concentrate on this. right? So what it does is, again, it will send a p comma q to a p comma q. Okay. Now these are very special differential operators going from section of some vector bundle to itself, and these are called elliptic differential operators. So there is a technical definition of this. What do you mean by elliptic differential operator? So I don't want to get into that, but there is a theorem from analysis, completely analysis, saying that. Okay, I think I jumped them there. So okay, let me first make some definition. So what you can do is you have operator and look at the kernel. Okay, so this is something called harmonic K forms. Okay, so there is a reason why these are called harmonic. These are in some sense maximal in some metric. Well, yeah. So these are the differential forms which have maximum norm in the cohomology class with respect to the metric this metric. So this is the kernel of this differential operator. And on the other side, I can make the similar definition. I can look at the this particular differential operator and take the kernel. These are called harmonic P comma Q forms. Okay, so I just denoted it this way to emphasize that it came from differential operator coming from Dolbeault operator, del bar. Now, what are these? So the importance of this is there's a theorem in analysis that says that if you have some elliptic differential operator from sections of vector bundle to itself or some other differential operator, then this there is this target, this or AK of X will break as an orthogonal sum into the kernel and the image. Okay, orthogonal sum in the sense of metric. These are perpendicular to each other, and this is a decomposition. So every element will decompose at a sum of two such elements. Okay. And on the other side, similarly, since this Dolbeault operator del bar, that is also elliptic differential operator. That tells by that theorem that AP comma Q of X will again break as two pieces: the kernel. Okay, I've forgotten the partial there, and the image under the operator, and which is again orthogonal sum again with respect to the metric. Now, now we relate this to the cohomology. So again, on the left hand side, if you look at this relation, and HK dr of X is exactly the look at the closed K cycle. Well, cycles differential forms which are going to 0 under D modulo the image, right? Which is this degree K Rham cohomology. This you can identify using this formula with this K harmonic forms, because this will be in the boundary, right? They will come from the image of the previous differential operator. So you get every cohomology class here will have a unique representative as a K harmonic form, and this we all identified this vertical arrow as a singular cohomology. So what we have done is we have identified singular cohomology with C coefficients with K harmonic forms. Okay. And on the right hand side, what we can do is we do the similar thing. So this we already identified, right? This is vertical isomorphism using the Poincare lemma for Dolbeault operator, that Qth cohomology of omega p, the holomorphic p forms, as the cohomology of the Dolbeault complex, and this I can identify with the harmonic p comma q forms because of this statement. This is decomposition. Okay, so this is going to be quite useful, identifying this, and this is exactly what will give us the Hodge decomposition. So now there is a slight technical problem, that what is going to happen is that this differential. So if you remember that this Laplacian delta D is an operator from AK of to this. Now AK of X has a direct sum of this APQs, right? So if I evaluate this differential form on a element of the type P comma Q, it may not go to a differential form of the type p comma q. Okay, that's a problem. But it certainly takes a degree k form to degree k. But again, and on the other side, this differential form, the Dolbeault Laplacian, it will take a p comma q differential form to p comma q differential form. So it preserves the type, right? So in general, delta d may not take a p comma q form to p comma q, but this other Laplacian will take p comma q form to p comma q. So this is where I have to use the Kähler metric structure on the complex manifold. Okay, so up till now everything is fine for complex manifold with the Hermitian metric, but now let's assume that you have compact complex manifold with a Hermitian metric. Now this is where the magic happens, so to speak, that the differential operator, if you let's say if you restrict this to p comma q differential forms, and you can apply both the sides, then this thing is a 2 times that operator, just a scalar. So you can now check that if I evaluate delta, if with these assumptions, right, with the Kähler metric, if you take a p comma q form, it will go to a p comma q form, because that's what this guy does. Right, now we just put everything together, and so X is a compact complex manifold with Kähler metric. Then we identified hk of x with hk of x comma c by the decomposition theorem that I earlier stated via Rham cohomology. And on the other side, we identified this piece by piece to this, again by applying the theorem, decomposition theorem of the elliptic operators for the Laplacian coming from Dolbeault. Okay. And because of this identity, this hkx will identify with the p comma q, the p comma q type harmonic forms. Okay, this exactly the equality will happen because of this identity. And
can you explain this slide again from the beginning?
Which part?
From the lemma itself.
So the point is that before this, like without the Kähler metric assumption, what can go wrong is that, so you have these 2 differential forms on, let me go back a bit, from ak of x. So the ak of x, there is this delta d, and this apq is a subspace of this.
Right.
Now what can happen, what can go wrong is that if I take a differential form of the type p comma q sitting inside this and evaluate delta d on this, I may not get a p comma q form. It will go in some other degree, other type. It might in general. And what this is doing, this is making sure that p comma q form will go to p comma q form, this Dolbeault operator Laplacian. Okay. Now with the Kähler metric assumption, so that's what I was sort of recording here, that delta d may not take a p comma q form to p comma q, where p plus q is k, but the other one does that. Now with the Kähler metric structure, what will happen, there are entities that come up with the Kähler metric that will guarantee that with all this, for all the operators that are involved, like all this adjoint operator, star operator, they will have all the ends of relations with them.
Is there an easy way to see this relation?
I think this is a very just a calculation. So you just have delta d is a sum of 2 things.
Okay.
Delta d is a particular operator like this. And there is a explicit operator like this. So you just evaluate, and you have to play with the metric, play with this metric, adjointness. So there are all kinds of identities that one has to use. So it's a very
Kähler thing get used there to prove that.
Right. So the Kähler metric, so that will give a separate operator.
I see.
Giving by cup product. And there are some identities that play around. So it is, I have not recorded them here.
Okay, it's okay.
But I can give a reference. So for example, the reference I found quite useful was this. IISER has a book, complex geometry, Hodge theory and part 1, I think.
Claire
so I think Claire IISER. So there is a chapter where she does all kinds of calculations and checks the details, like all these identities. and it is written much more very clearly. So but it's a very calculation based proof.
Yeah, I understand.
And so we just put it together. So what we got is that we identified a singular cohomology with complex coefficients via harmonic forms, which are decomposed because of the Kähler structure. And we identified this vertical thing by a Dolbeault cohomology using the complex manifold structure and so on. So what we got is that we got an isomorphism between HKX, C with this decomposition. Okay, this is exactly the Hodge decomposition theorem. Right. So now it can, what we do is we just write HP, X, C. So as HPQ, where HPQ we think about it as actual subspaces. So it's not some isomorphism, some abstract isomorphism, because these are abstract isomorphisms in some sense. This vertical isomorphisms, because they come from some Sheaf theoretic nature, a cohomology business. So we are going to identify HPQ as the actual subspaces of these things, which are Rham cohomology classes represented by closed forms of type P, Q, which came from this harmonic forms. Okay. And now we can check that there is a symmetry. So if you think about HK of X, R, which is a real singular cohomology with real coefficients, tensor with C, there is a complex conjugation on C. Okay, and just entity on this piece. This will take HP, Q to HQ, P. So this will exactly follow because you are identifying this HP, Q as cohomology classes coming from harmonic forms of type P, Q. And if you take the conjugation, it will go to a Q, P harmonic form. Okay, and that is how the HPQ will go to HQ, P. Okay, so this is the Hodge decomposition theorem. We have identified, we have broken it into pieces where there is some sort of symmetry between these pieces, HP, Q. Okay. Now, Hodge numbers are exactly, so there's something called Hodge diamond. So HPQ is just a definition. Okay, I'm not. Okay, so for some reason I didn't do a definition. HPQ, H upper P, Q is just a dimension of this as a complex vector space. Okay.
Of
and
this
because
direct
of this, sorry,
of this direct something, Reddit thing.
No. So the dimension of this total vector space is the Betti number, kth Betti number, and I'm defining dimension of HP, Q, lower HP, Q, or lower H to the power P, Q as a dimension of this thing. So you are writing Betti number as a sum of this Hodge numbers, HP, Q. That's what. This is just a bookkeeping. And there is a symmetry, so you can sort of visualize it as a diamond, right? In degree 0.
So each row sum up to the Betti number, right?
Exactly. So kth row will sum as a kth Betti number. This is the middle one. Yeah. And we just noted by symmetry HPQ is HQP. And of course, again, you can notice that if you have odd Betti number, since because of this, like let's think about H1. H1 is the sum of these two numbers, and by symmetry H10 is H01. So the number you get, the odd Betti numbers are even. These are some integers, and they are paired up. So odd Betti numbers are even. And okay, I guess I'm going to finish earlier than I anticipated. So okay, so I want to end the talk with relating it to the trimester program by giving a definition of the complex manifolds. This Calabi-Yau manifold is of the Hodge numbers. So I guess you have already seen the definition. Calabi-Yau manifold is a complex manifold of dimension n, where the HP0 Hodge number for P between 0 to n is 0, and the canonical bundle is trivial. And for Calabi-Yau 3-folds, you can visualize a diamond very easily because of this condition. This is just 1. This is 1 anyway, and the only non-trivial numbers that will appear are this. And amongst these, this is same as that because of the symmetry. and this is anyway sum of that because of some pairing, and right, some Poincare duality. So now the only non-trivial numbers associated to complete Calabi-Yau threefold are these H11 and H21. Okay, and now the general question people, I guess it will come up in this sort of next lectures, I guess, where people want to understand what are mirrors of Calabi-Yau threefolds, and you can say two complex threefolds are mirrors of each other if H11 of one of these guys is H21 of the other. So in some sense, we are getting a mirror image of the Hodge diamond associated with threefold. Yeah, thanks. I think
it's good. Thanks. Do anyone have any questions for Rakesh? Shan?
Hi Rakesh, no questions, but it was real nice attending your talk.
Right.
Thanks so much. Yeah.
Thanks.
So there was some conjecture related to some of these numbers.
Right, I think I guess you're referring to this. There was a conjecture saying that if it is the Euler characteristic of these guys, that one, right? This unbounded, that one. Yeah. Yeah. Apparently,
these numbers are easy to calculate according to you.
No. In general, Calabi-Yau threefold. So I guess if you take a particular example, like if the threefold comes from some hypersurface or something, some explicit hypersurface, there are ways to calculate this Hodge numbers in terms of other structures on them. But I think in general, I don't think there is a sort of recipe to come up with these numbers. There is a Sheaf cohomology of some differential forms. I guess if the complex manifold is like very non-explicit, or the algebraic variety is non-explicit, these are difficult to sort of calculate explicitly. So there is all kinds of study where they do. I mean, if you've seen this something called generating function business, where if you have some combinatorial problem and you want to understand the number of certain things, you put them in the generating function, like form some power series and try to understand the power series. Like put them together and try to understand them together, not individually. So similarly, there are people who do these things. For example, there's something called Hodge polynomial.
I see.
Where you form a sort of double two variable polynomial with coefficients like t to the power, like p comma q degree coefficient is this HPQ. And then there are all kinds of things that you can play with these polynomials and say make some statements. So there is a study around such things. But individually, it's difficult to track them, like to explicitly calculate given any arbitrary complex manifold.
I see, thanks. If there are no more questions, let us thank Rakesh again. So, should we discuss something after stopping the recording? Susan, you want to?
Yeah, sure.